All right, so now we move on to lesson 26, waves in one dimension. This is the third lesson that's in Unit D, which is waves in simple harmonic motion. And we're going to go into what are mechanical waves, and then we're going to loosely mention electromagnetic waves, which is physics 30, but primarily we're going to focus on what are mechanical waves and what are the things and properties and kinds of mechanical waves that we can mention. Now, first and foremost, when we talk about waves, waves are going to be energy carriers. So they're ways of transmitting energy in some sort of medium or through some sort of medium, specifically when we talk about mechanical waves. So that's going to be that note we highlight here, where waves are energy carriers, and through this vibratory motion, what we're going to see is that these particles are going to pass their energy from one place to another, and it can happen in two different patterns when we talk about mechanical waves. Now, again, as mentioned right off the beginning of the lesson here, the electromagnetic waves, this is going to be a physics 30 concept, so we'll save it. And it essentially is, if we take light and the motion of light and how light moves, it's going to move through the vacuum of space, so it doesn't require some sort of medium. Whereas when we talk about mechanical waves, these are the waves that require some sort of medium. And by medium, what we could simply say is a material of some kind. That's the way I kind of reference it, is when we talk about this medium, whether it's air, water, a string, spring, metal, rocks, etc., this is some sort of material. And so you could write that in as this kind of a subnote here if you really wanted to. Medium, you could draw an arrow to it and be like, this is just the material it goes through. And so I'll make sure I note that here. Okay. Now, if we know mechanical waves involve some sort of medium or material that's transmitting this energy, then we can break it into the following two types, which we're going to get very specific on. The two types of classical mechanical waves are transverse waves and longitudinal waves. Starting with transverse waves, when we look at transverse waves, these are the waves that their particles vibrate perpendicular to the direction of the motion of the wave energy. Meaning, if I looked at the direction of the motion, let's say it's from left to right, the particle movement would be up and down, and vice versa. If the motion of the particles, or if the motion was up and down of the wave, then we would say left and right is the motion of these particles. Now, there's two important things to note about this before we actually see some visuals. Transverse waves have crests, which are positive amplitude away from an equilibrium position, and troughs, which are these negative amplitude positions, which are below the equilibrium line. Now, the combination of these, or even individually, these can make up what we call transverse waves. Now, let's see a couple visuals of this. So first and foremost, in the notes, they give us this very, very classical depiction of a wave, which can be followed along as this sequence of positive amplitude, negative amplitude, and that pattern could continue on and on and on. What we really want to annotate on this diagram before we move into more conceptual pieces of this is, suppose we look at the components here specifically dealing with particle motion. They indicate that if I have any particle on this wave, it would be symbolic of some sort of up or down motion. And the way I'm going to do this right here is I'm going to fill in a couple dots representing different particles, and I'm just going to represent what's actually happening in terms of the motion. So it's not that these particles are going, left to right and they're following this trajectory. What they're actually doing, just like depicted on the left there, is each of these particles are going to be going up and down and up and down, and they're going to be moving in that up and down pattern, passing their energy from one particle to the next. And the wave that we see, or this overall trajectory of this wave, is just the energy being transmitted from particle to particle. So that's the pattern in which this happens. Now, again, when we look at the amplitude, what you may want to do is, we see that we have a crest or a high point, but in your notes, what I'd recommend doing is from that high point to what we call the equilibrium, I would put a positive A, implementing that this is positive amplitude. So maybe I'll even write the positive just a little bit lower here, positive A, just to make sure that we can get that in there. Now, on the other side, we see a trough, a low point from the equilibrium, and then again, from that very high point to the equilibrium, we can write this as negative amplitude. Now, just to make sure that we're specific on this, when they say direction of wave, I would even put an arrow this way and say that this is the direction of the speed of the wave in the left-right pattern. And then last thing we want to put is that this is our equilibrium, or it's the equilibrium point from where the object is displaced, or from where the particles are displaced. So they'll either be displaced positively or negatively, and then we see this constant oscillation of these particles, or these constant perpetual movement of these particles as it goes through this medium here. Now, in the diagram below, essentially what they do is they take some sort of rope that's attached to a wall on the end, and what they do is they give this object a pulse. And we're going to get more specific about what that means, but they're going to give this thing some sort of pulse to the right. And by giving it this pulse to the right, which is the combination of the up movement to then the down movement, this is going to create some sort of overall, it could be simply just a pulse, or it could be a wave or a wave train, which is a sequence of pulses. Again, we're going to get more into that. But what this sets up is this idea that we're going to get these particles that have up and down trajectories, and it's sometimes hard to tell just based on like a stationary image, what are the particles actually doing. So in class, what we would do is we would pull up the PhET simulations, but on top of the PhET simulations, what we also did in class is the following. You may want to grab a scrap piece of paper or even just write this in the margin, which I had everyone in class do. So we're going to go to this separate piece of paper or the margin on your page. And what I'm going to first and foremost do is I'm going to try to just draw a simple wave that is some sort of wave in just a standard transverse wave. We're not going to specify a certain amplitude or a certain wavelength for this case. I'm just going to draw a very basic transverse wave where we have crests and troughs and crests and troughs. Okay, now the other piece I'm going to draw on this is the equilibrium line, which goes directly down the middle, or it separates the positive amplitude to the negative amplitude. Now, what we would do in this diagram is we would label all our crests, which are those high points. So crest, crest, and then over here would be a crest. Our troughs are these low points. So we have trough, trough, and trough, which are all the low points. And then when we look at this piece here, the one thing I really want to specify and go into detail on is suppose that we have the direction of the wave going from left to right. And so I'm going to indicate that in the following way. The speed is going that way, and this is the direction of the wave. Okay, so we have a left to right motion of the direction of the wave. Now, if this is the case, what they may ask you, and this is going to be linked actually in the description as well, is a separate video that goes into this as well. How do we indicate if a second passes or some sort of time passes, where would the particles be given that the wave continuously is moving and we want to look at this thing a second later? If time passes by some margin, what we're going to do is we're going to write the new wave, or we're going to write where the new wave would be doing the following. If the direction is from left to right, then if some uniform time passes for all these particles, I want you to just draw uniform arrows that are going to the right. Because if we know that the particles are being pushed in terms of, we know they oscillate upwards and downwards, but if this is a second later, what we want to do is we want to symbolize that the overall wave pattern would be somewhere to the right-hand side. Because realistically, the particles are going to keep going up and down, and their position is going to change. And so an easy way to sketch out our new curve is going to be, let's draw a bunch of arrows representing some time later, and all these arrows should be the same length. And then what we can do is we can just simply play connect the dots. We can draw our wave that goes in front of all these green arrows. And the major thing you want to do is, as you do this, make sure that your crests and troughs are at the same height. What I mean by that is we shouldn't be going higher than the point that was originally there, or higher than the positive amplitude original, and we shouldn't be going lower than the original negative amplitude. It should follow exactly. And here's the number one thing I want you to notice. By doing this simple depiction of, we have a bunch of arrows that follow the direction of the wave's motion, what we notice is that we see the original curve, which is in black, and then we see this new shifted curve that is a little bit more right of the original curve, but it follows the same wavelength, the same frequency, the same period. It's just shifted in front, because this is supposed to represent what would be happening a second later to this given wave. It would look like the one in green. Now, what I'm going to do, and what I highly recommend you do, is I want you to draw a couple different positions here. So first and foremost, I'm going to draw one of the particles at A. I'm then going to draw a particle at B. I'm going to draw a particle at, let's say, like C right here, not to be confused with crest. And then I'm going to draw another particle on the original right here. Okay, so I have 4 different positions, and these are A, B, C, D. These are just random particles that would be on this given wave, or a part of this given wave. Now, what they could ask is they could say, well, given a second later, now that we have this green sketched wave, which represents a second later, where would particles A, B, C, and D be located given that this wave has shifted or that some sort of time has passed? Remember, in a transverse wave, the particles can only move upwards and downwards. They only have that up and down motion, or if this was inverted, we could make the direction of the wave, let's say towards the north, it would mean that the particle movement would be east and west. But to keep it simple, we always typically do the direction of the wave in terms of left or right. And then from here, what we want to be thinking about is if A is transformed to the new graph where the new position of the wave is, where would it be? Well, because A can only move upwards or downwards, it means it's going to shift down to this green line. And here's where A's new position is going to be, directly below on the new line. And I'm going to call it A prime. So that's sometimes what they do in math or physics is they call that new position A prime or whatever variable prime. Now, for the case of B, if it was originally here, the new curve or the new shifted curve or the new position of the wave is at the green line. So I'm going to put now that B has shifted upwards, and this is going to be B prime. C is going to be down here on the green line because it can only shift vertically, and to get to the new position, it has to go down. And then lastly, D has to go up in order to get to its new position here. So all the primes are the new positions of those particles, and then all the original A, B, C's, and D's without the prime are the original positions where it was originally at when the wave started. So hopefully this provides a little bit of guidance of how to sketch these graphs, because it is really important to determine what's happening to the position of these. And just to be even more clear, before we even move on, I just want to make sure I use an arrow to indicate where they're going to. So A goes down, B goes up, C goes down, D goes up. And again, we can then even get more specific and we could talk about like regions of decrease. So anywhere on here, in order to go from the black line to its new position, all of these would go down. Same with the positions. Any particle that would be on this position where A is, these would all go down. And then any position which would be somewhere in this B range, or any position where it'd be in the D range like this, these would both have to go up in order to get to the new line. So if you kind of see the pattern or the general trajectory of what's happening, that might be an important thing here. Now, I know this can get a little messy when we start really annotating all this stuff, but this is an important skill and you should be able to do this. Okay, now we're going to go on to longitudinal waves, which is the following. Longitudinal waves are a little bit different in the sense that they have their particle motion parallel to the direction of the motion of the wave, or to parallel to the overall energy movement within this wave. Now, it's composed of the following. We have either compressions or areas where they are condensed or more concentrated together, or we could have areas of refraction or refaction, and this is areas where the particles are instantaneously farther apart and they are separated by some sort of region. And so I'm just going to make sure I retract that highlighter just a little bit, and there we go. So instead of the particles moving up or down or in a perpendicular pattern to the overall motion of the wave or the energy of the wave, now they're going to be moving in the same direction or parallel to that direction. I shouldn't always say the same, but they're going to be moving parallel to it. Okay, now let's take a look at what that means in terms of the diagrams here. So here's a simple couple examples here, or a couple things we can look at. One is the idea that we have some sort of spring which is on a horizontal plane and it's being compressed and stretched and compressed and stretched. Again, compressions are simply these areas of high density of the particles or high density of the given medium, as we're going to call it. What is the medium? The medium is simply just the spring itself. So spring, because I believe this is a spring, maybe it's a slinky, but it's a spring, is equal to the given medium. This is the thing that's transferring the energy. The compressions are where this spring gets compressed together by nature. And then when we look at the rarefactions, these are the areas in which we get that separation. I don't want to cover up that terminology, so I'm just going to make sure I kind of box that there. It's these areas of separation. Now, again, just like before, wave motion from left to right, it could be right to left, it could be left to right, it could be one of those two, it could even be up or down, but typically when we're learning these, first and foremost, we like to keep it horizontal and either left or right in terms of the wave motion. Particle motion, it's going to be left and right because it moves parallel with the given motion of this, or given velocity or the energy that's in the system. Now, we could look at it rather than being a spring, we could consider it to be like some sort of particles that move and cluster together. Well, compressions are all these areas in which we get this clustering or this gathering of the particles, this condensation of the particles together. And then refractions are all these areas where we get this nice separation or this area of kind of like open null space here, if you really want to call it that. There still is particles, so it's, I shouldn't say null space in the case that there's nothing there, but when we look at this, we're going to consider that the particles are nice and spaced apart. Their energy is dissipated across a larger region than the areas of compression. Now, something to note here, and we're going to get more into this in terms of wavelengths, which are lambda, but when we look at a given wavelength, just to kind of forward when we get to that topic, one wavelength is considered from the same region or same type of region to one region, either left or right on this. So when I go from a compression region to another compression region or specific point on that compression region to a specific point in another compression region, which we call one phase away, this is one wavelength. Similarly, I could also say, if let's say I'm at this position in the refraction and I go to that same position, but one phase over, either left or right, this is also what we call a lambda or a wavelength away. Now, there's infinite combinations of wavelength in this case because you could pick an infinite amount of different spots on this line and connect them to an infinite amount of spots, one phase either to the left or the right, and this would give us some sort of lambda. So it's kind of a very broad, but I will say compression to compression or rarefaction to rarefaction, these are the easy ones. Same with when we talk about, we're going to look back to our transverse waves. The wavelengths are very simple in those cases. Now, let's just take one more close look at this in terms of, let's say I have some sort of spring or slinky, if I even want to have that. And in the original position, we give the object some sort of pulse, just like we did with the transverse waves, but in this case, we're dealing with longitudinal waves. So the normal spring is as is, and we push on it downwards towards the bottom piece here. Now, what that's going to do is when we push on it, it's going to gather together the spring in this area of compression. So this is a compression, this is a compression, this is a compression, and this compression is moving its way down the line. And as I continue to apply new energy forms, or as I apply new forms of energy, what we may see is that there's going to be this idea of multiple compressions or just areas where the spring is going to naturally compress back to. Now, as I look at this piece here, I want you to be thinking about all of this spring down here, where it looks like exactly that it's in its natural state. You can even just write that in the margin here and be like, this is the natural state of the spring. And I'm just going to simplify it as natural state. There is no energy that has reached this point here, but when the compression starts to move through the spring, it's then going to create these areas of rarefaction, which are these areas in which the spring is separating. And so I would even classify it as like in this kind of region here, this kind of region here. These are all examples of that rarefaction where it's separating apart from each other. And so maybe I'll even be very specific. Here's our compressions. And then here is our rarefaction. There we go, just so we have a complete diagram of what's happening. So we have the condensing of particles or condensing of particles as the energy moves through. We have the rarefaction, which is the separation after that compression has moved through. And then we have natural state, which is just the energy hasn't reached that piece yet. Okay, now let's go more specifically into wave pulses and waves, or pulses and waves or wave trains. Now, in the case of a wave pulse, what a wave pulse is simply I just disturb or I do a temporary disturbance to the end of whatever the medium is. So in this case, it could be a string, a slinky, a chain, realistically, whatever it is, maybe even water, the surface of water. When we look at this, it's a temporary disturbance where we only provide a simple oscillatory motion that starts energy in the system, but it's not a sequence of that. When we look to a wave or a wave train, a wave or a wave train is where we continuously apply pulses. So it's not just one pulse or it's not just one disturbance, a temporary disturbance, it's multiple disturbances being chained together. And through these multiple chains of disturbances, we get waves or wave trains, and then this is going to lead us to having certain amplitudes. So amplitudes can either be positive or negative, but it's the displacement away from the equilibrium position. Now, let's actually represent that in terms of the diagrams below. We're going to first of all look at what a pulse is, and then we're going to look at a wave train or a wave. Now, if we're specifically looking at a wave pulse, on these diagrams, what I would like you to do is I want you to draw an equilibrium position right along the bottom here and an equilibrium position right here. Because this is where the string or slinky in this case would naturally want to rest given that there is no energy. Now, here's what I asked in class. If we have a positive wave pulse or something with positive amplitude, like in this first case, what does that mean in terms of what does the pulse have to be? And a lot of you correctly said, well, first I would have to move the object quickly up, and then I would have to restore it back down to the equilibrium. And what this would do is it would generate this quick pulse where we don't go below the equilibrium, we're staying above the equilibrium, but it generates this energy, which then is transmitted with this certain positive amplitude, which again, we can say that the positive amplitude is representative of the energy. That is really important here, is to tie this together, is amplitude is related to energy. And so I'm even going to draw an arrow over here and be like, energy is amplitude. Maybe not necessarily like equal, because when we talk about amplitude, it's typically in a measurement of a certain distance and energy is in joules, but we do want to correlate these things together, and we'll go more into that very shortly. When we look at a negative wave pulse, if this is from left to right, to get a negative wave pulse, instead of going up and then down, what we have to do is we initially have to pull the string down, and then, or slinky, or whatever the material is, whatever the medium is, and then we have to restore it by pulling it up directly back to the equilibrium. Now, if we only do this one time or maybe two times, these are just individual pulses. This isn't a wave yet. This is just a wave pulse, or an individual set of pulses that send some sort of energy or some sort of amplitude down the line. Now, here's where we move into that idea of a wave pulse that eventually becomes a wave or a wave train. If we sequence together multiple together, I want you to draw a horizontal line again, right here, indicating that this is our equilibrium position. So we should make sure we put that piece in here. So this is my equilibrium. And I'm even going to make sure I write that above here as well. I probably forgot to do that, which I did. Yep. So I'm going to make sure I put equilibrium, which is very, very critical, representing this natural rest position or that rest state. So we get this equilibrium along this position here. Now, when we look at this, again, to create this sequence or create this sequence using pulses, what we would have to do is we would have to go up, we would have to go down, and then we would have to go back to that equilibrium position in order to create this pattern. And the reason is because in order to get positive amplitude originally, we would have to give it a pulse in the upwards direction. To get the negative amplitude, we would have to then pull down through the equilibrium to the negative position, and then to get the slinky or the spring to then restore back, we would basically just restore it back to the equilibrium, and that would create that positive, negative, and then back. Now, if we get a wave that is in perpetuity, or it just continues on and on and on with this infinite sequence, again, we can write it as the equilibrium position is right in the middle. And so I'm just going to short form it as EQ is right down the middle. And again, maybe I'll even just write it in red here just to symbolize that we have the same thing here. And then let's say I look at this wave that is going in perpetuity because the endpoints look like they just keep this pattern going and going and going. What this would be is a sequence of pulses where I'm just continuously going up and then up and down, or I'm going away from the equilibrium, down past the equilibrium, away from the equilibrium, back down from the equilibrium. And through this sequence of pulses, you'd be generating positive amplitude, negative amplitude, positive amplitude, negative amplitude, and it would continue this pattern going. But this is a process that's happening in perpetuity. Now, I'm going to backpedal this just a little bit because I want to maybe mention something here. What if my wave started right here? And the thing I proposed in class is I said, if the wave starts here, what was the original pulse pattern? And lots of you correctly said, you were like, oh, in order to get the negative amplitude, I would have had to go down, and then I would have had to go up from there, and then continue that pattern of down and up and down and up, and continue it from there. But in order to start this wave, if it starts at the blue line and the direction of the movement is from left to right, it must have been that I displaced it from the equilibrium downwards first and then started that pattern of oscillation. Okay, now again, all four of these examples that we just worked through are transverse waves. They're where the particle movement is up and down and it's perpendicular to the direction of movement. So it's not that particles are having a fun time flowing along this line. The energy goes along this line, and the direction of movement is along this line. But when we talk about the overall motion of the particles in this situation are purely moving up or down at any given moment along this wave train or this wave. So we got to be very specific about that. All right, now we're going to go forward into some more terminology here. Specifically, what I want you to do is before we actually talk about any of the terminology on this page, I just want you to go to the bottom of these and connect them. In your notes, you probably have the same thing where it cut them off a little bit. We want to make sure these are connected and so that this forms a full wave or wave train. Now, we want to go into this idea of what is a wavelength and what is period and frequency and how is that related to this unit. So for any type of wave or any sort of classic wave, the wavelength pronounced lambda, which is this kind of fancier symbol where to draw it, here's what I said in class with this, you can draw an S or kind of like a squiggle and then a line off of that. A squiggle, a line off it, a squiggle, a line off it. You may want to practice that a couple times just to make sure you master it. All the way through university, I drew it like this, which is, that's pretty ugly. That's not what we want to get out of this, right? So if you need to practice this, just make sure you do one squiggle, starting at the top, left to right, and then a line off of that. And it will take a little bit of practice to make sure it's good. Now, am I going to judge your skills on that? Probably not, but just to bring it up. So lambda is the wavelength, and essentially what this is it's the distance between any 2 points that have the exact same phase or position in the wave. What that means is that I should be able to go on any given wave and then pick 2 points that are in the same position, but maybe one phase to the right, one phase to the left. And so when I look at this, one wavelength could be symbolized by crest to crest. That would be a prime example of one lambda. Another lambda that we could do is trough to trough, which is kind of what they're doing over here, but I'm just going to really re-emphasize it here. Trough to trough, or from here to here, could also be considered one lambda or one wavelength. Now, here's where that idea of infinite combinations comes in of different wavelengths. I could also do a wavelength from here to here. These are the same position, but one phase away, and so I can draw a line connecting these and be like, that would be considered one wavelength. Let's say I look at a position like this, down here. Well, one position to the right would mean that this is my new spot, and this would therefore become one lambda. So same position on the given wave, or in this perpetuity of the wave moving, it would be in the same position, just either to the left or the right from that given first position. Now, some other question I could ask you in this situation would be, what if I gave you this original line or this original wave and said, how many wavelengths is this? And so what you would have to do is you would have to start at one end and then count the number of wavelengths. And so I'm going to highlight in yellow the first wavelength, or actually I'm going to do green and blue. So here is representative of one wavelength. That would be one wavelength first and foremost. A second wavelength would then continue the pattern. And so there's 2. Here's 3. And then lastly, we just have this little bit remaining, but it's not really a full wavelength. It's not really a half a wavelength. It's almost like a 0.6 or a 0.7 of a wavelength. So we look at this and we're like, here's one wavelength, here's 2 complete wavelengths, 3 complete wavelengths, and roughly, you could say this is a half, but I would say it's a little bit more, maybe like a 0.6 of a wavelength. And so the total number of wavelengths in this case, number of lambdas, as I'm going to call it, is equal to roughly, and I should say not equal, but maybe roughly equal to 3.6, or even like 3.7 would be okay. And that's just because it has that extra little bit that goes below the equilibrium. So it might be just a touch more in this case. That is a very important skill to be able to do, is count the total number of wavelengths, because you should be able to analyze that and be like, okay, I should figure out what one wavelength is first and foremost, because that's the most fundamental skill, and then the total from there. Now, what we could do is we could take out a ruler and we could confirm that these are all a wavelength of 29 millimeters. And that would just be by taking a ruler and measuring these all. But the big takeaway is that as long as you've properly labeled what one wavelength is, it shouldn't matter what 2 points you pick on the given wave, it should all be the same. Now, period and frequency, we've talked a ton about this before, so this isn't really anything super new, especially because we've dealt with this in previous units, and even the beginning of this units with pendulums and springs. But to be more specific to this section, or be more specific to waves, the period is the amount of time it takes for the wave to travel one wavelength. And again, what is one wavelength? This idea here, it's one lambda, or this kind of fancier symbol that we just introduced. Now, the frequency is how long it takes in order to complete one of these given wavelengths. And so the number, and let me backpedal that a second. It's the number of pulses or vibrations or wavelengths which occur in 1 second. So how many wavelengths would pass by, or how many wavelengths exist in a given region for a certain amount of time. And on our formula sheet, we've been given this formula sheet even in our past unit, even in the beginning of this unit, so we're very familiar with this. Now, before we go into a bit of a thought experiment, I just want to talk about a little bit about this theory that's really important from the notes, and it's the following. And I highly recommend you star this because it's a massive concept from the waves that we're going to introduce here, specifically dealing with our classical waves here. So when we look at these waves that travel through mediums, specifically, or I guess we could say this generally, but specifically for our classical waves here, we look at these and we see that the wavelength, period, and the frequency do not depend on amplitude of the wave. And I want to be very specific about that using the diagrams, and then we'll even say more about that in a second. If you look at these two diagrams that are on the right, the one thing you're going to notice is that the same amount of wavelengths are in each of them, the same amount of frequency is in each of these, but the amplitude is different. We see one has a greater spike or a greater peak and trough, or crest and trough if you want to use that language, and this one has lower crests and lower troughs, but they accomplish the same amount of wavelengths and frequency in that given window. Now, what is that all about? When we look at this, if wavelength, period, and frequency do not depend on amplitude, then what is amplitude? Amplitude is symbolic of the energy of the wave. And so when we look at this, how much energy determines the overall amplitude? So the greater the energy, the greater the amplitude. And then just to subnote this, the frequency, on the other hand, is related to the vibratory rate of the source of the wave. So the higher vibratory rate, the higher the frequency. This means that source, and I would highly recommend you write this down below here and maybe even start, that the source determines the frequency slash period, because we know that these two things are directly related. So I would make sure you write them in both like this. So the source, and when we talk about the source, what is the source? It's the thing that creates the wave pulse or the wave train or the wave. So that determines frequency and period. Whereas the amount of, and I mean, we to some degree we could say that the energy is also related to directly to the source, but we want to be very specific about frequency and period is determined by the source, whereas amplitude, it's not always determined by the source, in the sense that we can add or subtract energy out of the system through dampening or through some sort of accelerated process that gives us more amplitude over time. So one example that I like to think about is when we talk about increasing energy in a system or increasing amplitude, if you're pushing a kid on a swing, originally they'll be going backwards and forwards, kind of at a low height, backwards and forwards like this. But then over time, if somebody's pushing them from behind, what happens is they start low and they start climbing and climbing and climbing, and their energy gets greater. So we couldn't say that the energy is related to directly the source in a sense, because what we would be saying is that it's a combination of the energy that's already in the system of the kids swinging backwards and forwards and the push of the energy added. Now, that may be not the best example, but it does the trick. When we talk about the amplitude remaining consistent, that might just be where we're in a closed vacuum. There's no friction, heat loss, or air resistance. So the energy is being maintained, and we get this nice, perfect balance of a transverse wave like this, or even we get a nice longitudinal wave where it condenses and then it separates, and then it condenses and it separates, but it all happens in the same margin. But again, the big takeaway we want to have here is we want to look at this and be like, the amplitude is related to the energy. The greater the amplitude, the greater the energy. The less the amplitude, the less energy. Now, going over to the diagrams here, I'm just going to provide a rough example here. So something with greater amplitude, maybe like ocean waves. And then for the smaller one, you could be like a pebble in a pond. So clearly, we know dropping a pebble in a pond isn't going to create seismic ocean waves. But what could be true is that the period and frequency and the wavelength might be the same in certain conditions between ocean waves and a pebble in a pond, but something like a tsunami generates a lot more energy, therefore a lot more amplitude. Now, again, that might be a bad example as well, but it does kind of serve that purpose of we have different energies in the system that can share the same principles of wavelength, period, and frequency, but not the same amount of energy. Okay, now going to our next page here, here's where we go into the universal wave equation. And this is really important for the algebra part of this unit. There's not a ton of algebra, it's mainly theory, but when we look at this, we should be able to use this equation to help us solve for all wave types, whether that be electromagnetic or whether that be transverse or longitudinal waves. Now, when we look specifically to different mediums or different materials, they travel at different speeds. The magnitude of the speed depends on a number of factors. For instance, if we look at sound waves that travel through rocks, they'll travel through faster as sound waves through rocks than they will through air because rock has a denser medium than air. Another factor is rigidity, or how rigid the medium is. The faster the medium of, or the faster the speed of the wave in that medium, because as we think about things that are more dense or more rigid, that means that there is tighter packed molecules, tighter packed particles, and that tighter packed particles are going to more efficiently transfer their energy than something like air that's more separated and will have less contact between the particles in the air, meaning less efficient transfer of energy, and so we don't see the speed as fast. Now, moving into the connection from kinematics into this unit, we know that the speed is determined by the change in distance over change in time. That's pretty typical. And so the speed being some uniform speed, because this is our uniform motion equation, we have some distance to travel over some time. Let's create a parallel to our unit. Here's what we're going to do. Right away, the change in distance, what is it? It's lambda. It's how far the wave goes in a given amount of time. So we look at this and it's like lambda from one phase to another is that change in distance. So change in d is equal to lambda. We know that our change in time is the period because the period represents how long it takes to complete one wavelength. And so I'm going to write this as change in t is equal to period, or capital T. And then lastly, the only conversion they do is they say, well, if we know that period is related to 1 over f, or t is equal to the inverse of frequency, 1 over f, then it must be true that we can derive this final equation by the following. If I know speed is equal to lambda divided by 1 over f, so I'm just writing the division left to right rather than vertically, what I can do from math, whether it be 10C or even math 20, is I can write this as lambda multiplied by f, therefore giving me the final form of frequency times the lambda, which is our universal wave equation. And the beautiful thing about this equation, it's on your formula sheet and it applies to all waves. Therefore, it's given that name of universal because it applies to all waves. So if you're given something like speed and wavelength, you can determine frequency, you can determine period even. You can determine, let's say you were given frequency and speed, but not wavelength, you could determine wavelength. And lastly, if you were given frequency and wavelength, you can determine the speed of the wave, which is really nice. And there's a couple examples below here that go through that math, but realistically, there's not gonna be much that trips you up here. The only thing they could do that maybe would trip you up is maybe they give you period instead of frequency. Maybe they give you kilometers per hour instead of meters per second. And then maybe they give you something like centimeters instead of meters here. So they could play around with the units, but that's the only thing they could really do to like trip you up in these cases. All right, now moving forward into reflections and transmissions of waves. This is very important and it's our last section within this lesson, but it is very critically important. When we look at the reflection and transmission of waves, specifically, we're going to look at different types of boundaries, starting off with the boundary where we meet a fixed end. So some sort of medium is attached to a fixed end, and a fixed end means at the end of the line, it is attached to some sort of other like material. You could say this is a rope attached to a wall if you wanted, but the medium is fixed at the end, hence the name fixed. Now, what's going to happen is when we look at this piece here, we're going to consider this to be a positive amplitude because it's vertically up, or it's towards the north. So we're going to consider this by orientation positive amplitude. Now, I asked in class what would create this as a pulse, and lots of you correctly said, I'm going to move quickly up and then back down to the equilibrium, where I have to go up to create that positive amplitude and then back down to then complete that given pulse. So here's my pulse. And through that pulse, I send this energy down the line. And when it reaches this fixed end, a really interesting property happens, and it's mentioned in the notes here. So if you want to take a closer read on what I'm about to say, you can read it within here. But essentially, this endpoint acts as an anchor where you hit the endpoint. And what's going to happen is that the force generated, or this energy, is going to try and force this cable upwards. And so I'm going to label an up arrow and call this force number 1. Now, because this is a fixed end, unless there's enough force to break the string, it's almost going to hit this like brick wall of it can't progress any higher. And so by Newton's third law, we're going to see that the force is responded with by an equal and opposite force in the opposite direction. This is Newton's third law. You may want to write this in. So Newton's third law. There we go. And I'll make sure I correct that little third there to make sure it's more obvious. There we go. So Newton's third law, it hits this fixed end. The force or the energy is now all being applied up, but because it gets trapped, because it's fixed at the end, that force is responded to by an equal and opposite force. And with that, what's going to happen is that it's going to force this overall medium to meet back at the equilibrium very temporarily, but because there's an equal and opposite force, it now will be responded to by some sort of force that sends this back downwards in an inverse pattern where the wave that was originally upright is now inverted and it goes back in the downwards direction with the same energy, which is represented by the negative amplitude here. And so we see, if we zoom out on this overall situation here, we send a pulse down the line, or we send energy down the line as positive amplitude. It hits the fixed end and it gets inverted because of this Newton's third law, equal and opposite tug on the end. And when it gets inverted, it sends back the energy. Now, we're making a very broad assumption here, and it's the following. The energy in the original position, or the original energy symbolized by the positive amplitude, is equal to the negative A in the end. And what we want to make sure we note here is the following. If the positive A is equal to the negative A in terms of overall magnitude, it must be that energy was conserved. Now, this isn't always possible, and here's what I would say about this. If this was more real to real life, what we may actually see is that if that energy was originally sent down as positive amplitude, in the end, rather than it being directly conserved, you may actually see the amplitude is somewhat smaller, meaning we lost some sort of energy to friction, heat, sound, whatever it might be, but you would see a lower amplitude in the end. But because this problem, as we kind of go through the theory of this, we want to typically say that the energy is conserved just to kind of help us out in simplifying the explanation when we're first learning it. Now, this is for fixed end. It hits a fixed end, we get that Newton's third law, action-reaction force at the fixed end. On the opposite case, here's where we go to the second situation, which is what if we have a free end where it's now not restricted, it's not attached to anything at the end. Well, what's going to happen is that, again, we send some sort of positive energy or positive amplitude down, meaning we had a pulse that was originally up, then down, like this. It was a singular pulse that sent the energy down the line. Now, it gets to this endpoint here, and what we're going to notice is that the energy has nowhere to, it's not attached to a point. So it's not getting this Newton's third law of equal and opposite reaction. In fact, what happens is all the energy is getting lifted up at the endpoint because it's now transmitted its energy down the whole line. And because there's no more medium to go, it transmits all that energy vertically, and we get a momentary moment, or we get an instantaneous piece in which the speed is temporarily zero at this moment, and we have all of this stored as elastic potential energy. And so I really want you to write that in here. This is our elastic potential energy. Now, as we know from our previous section or our previous unit, potential energy is the potential to do work, or the potential for something to happen, in terms of this potential energy typically wants to move into kinetic energy at some point. So it gets stacked up, the energy is all increased, the energy is maximized into this potential energy at this point. And then what happens is, because it's not a fixed end and we don't have that equal opposite Newton's third law, it's going to send back that energy in the reverse direction, not inverted though, in the same pattern or the same orientation, back the direction with the same positive amplitude. Now, again, we're being very generous with this because when we look at this, in the beginning, we had that positive amplitude with some sort of energy generated by the pulse. It gets stored as elastic potential, it rebounds backwards, it comes back as the same positive amplitude. This means that, again, we're assuming that if the positive A is equal to the positive A in the end, it must be that energy was conserved. Now, if we look at the PhET simulation, which we probably will in class, the PhET simulation is going to show that typically I can include some sort of damping, as we're going to call it, and we're going to get more in terms of like what damping is in the next lesson. But damping is this idea that we're removing energy, or we're kind of taking energy out of this system through an external factor or an external force. So whether that be friction, heat, sound, I'm putting my hand on it, it could be a bunch of different factors. But what we may see in this is rather than a perfect amplitude coming back with the same height, meaning it's the same energy, we may actually see that this overall amplitude would be something less, just like the fixed end, because it's more realistic to real life that we would see a decrease in amplitude over time. But if we want to be very generous when we're first learning this, we're just going to assume that through this process of a fixed end, it's going to reflect back that overall amplitude that's the same. All right. Now, continuing forward, this is our last and most critical piece, and it takes all of the knowledge we just learned right before and it puts it together to talk about what happens if we mix mediums and we take energy and we apply it through two mediums where there's this transition point from one medium to the next. What we're going to see is that if we mix mediums, we're going to take some sort of rope and or some sort of material and connect it to another, and we're going to send energy down that line, and depending on the orientation, we're going to get some sort of partial reflection or energy that gets returned back to that same medium, and then some of it's going to be transmitted onto that next section. Now, what we're going to notice is the following. We're going to really detail this. Again, we could read through that note, and if you need to, read through that note afterwards, but I'm going to verbally explain everything that's happening theoretically here. If we're in a slow medium, let's consider this a chain connected to a rope, where this is going to be our chain, this is going to be our rope. The rope is the fast medium because there's very low impedance or low resistance to the energy through it. The chain has a lot of resistance to motion or a lot of resistance to the energy transformation. What we're going to do is we're going to assume that there is some sort of energy given to this through some sort of pulse at the end point here. And so again, just like in the previous examples, a pulse. We send a pulse down and it hits this fast point. What I would like you to do in your notes is just draw a vertical line right at this point in which it changes from the slow medium to the fast medium. As this energy reaches from the slow medium to the fast medium, one thing you're going to notice in particular is that if I go from a high impedance zone or a really restricted zone to then something with little restriction, it's going to flawlessly pass through that energy. And we can consider this to be a loose end problem. From what we just talked about, this is a loose end or an open end, if you really want to call it. And I'm going to be more specific when I draw this. It's right at this point in which those two meet. We're going to consider this a loose end or a non-fixed end. In a non-fixed end situation where we go slow to fast, there's not a lot of impedance, there's not a lot of resistance, so the energy gets transferred really nicely. And just like we've said in the note right above, some of that energy is then reflected back, but some of that energy makes its way through to the next medium. Now, I want to comment on something very specific here, and it's the following. The overall wavelength here, which I'm going to call wavelength 1, is equal to the wavelength in the end here. These two wavelengths are equal because they share the same medium. And so as long as we're in the same medium, the period, frequency, and wavelength should all be maintained. Everything in this slow region should be the same. But when we go to the fast region, there's less particle condensation or less condensing of these particles, less impedance to the motion, less resistance. And if there's less resistance, this thing can space out and we get a larger wavelength, which I'm going to call lambda 2. So particles can space out, the overall motion or the energy can space out more because there's less impedance, less resistance. So I'm going to write it as lambda 2 is greater than lambda 1. So the wavelength of the faster medium is greater than the wavelength of the slow medium because there's less compression. All right. Now, as we move into our next piece, we're going to look at the opposite situation. What happens when we look from a fast to a slow medium rather than a slow to a fast? So if I look from a fast to a slow, again, what I would recommend doing is just write a vertical line here. So there we go. And through this vertical line, we're going to consider this to be a fixed end. And so I want you to draw an arrow right to this point here and be like, instead of being a loose end, this is now a fixed end, or the situation in which we get Newton's third law. Now let's explain this. If I have some sort of positive amplitude that was given by some sort of original pulse on the end here, this original pulse generates some sort of wavelength and some sort of pulse that sends this energy down the line, and it interacts with this fixed end. The reason it's now a fixed end is because in fast mediums, again, we know that the wavelength that's here is a large wavelength. In fast mediums, there's not a lot of this compression or resistance, so the particles can easily move throughout this, or the energy can easily transmit through this medium. When it hits the slow medium, this is where it's interesting. Slow mediums are where it hits a large zone of impedance. So everywhere over here is a lot of impedance. And I want you to think about it as if this is the rope or the fast medium, and this is the chain. If you lift up a rope really closely and you lift it up, you give it a pulse, and it sends energy down the line, what you would notice is that when you go from the rope to the chain has a lot more resistance to that motion. It has a lot more inertia. It doesn't want to transmit the energy. And so what's going to happen is in the case of fast to slow, when we get the transmitted wave, yes, we're going to still transmit some sort of energy through, which will be this positive amplitude. But when we look at the reflected amount is going to be negative in amplitude. And so we look at this piece here and we're like, if I look at the pieces together now, when I hit that fixed end, just like we talked about in that section a couple minutes ago, the reflection or the part that's sent back is always reflected. The nice thing is in both cases, whether it be a fixed or an open end or a fast to slow or slow to fast, the amplitude that is transmitted through is always positive. We just need to really focus on what is happening at the end. Is it inverted or is it or we could say, is it reflected upright or is it reflected as an inverted amplitude? All right, now, the other thing I want to annotate here is that piece we did before. This wavelength or wavelength 1, this is wavelength 2. We want to say that the wavelength 1 is greater than wavelength 2 because in a slow medium, there's more impedance or more resistance to the motion or more impedance to the energy transfer. All right, lastly, we want to go into interference. Interference is this big topic which says what happens when waves cross over each other, or what happens when they meet towards each other. And in the notes, what they do is the following, and we'll go specifically through this. When two waves move in opposite directions and they meet, they do not reflect each other, rather, they pass through one another. So that is a very important thing to note. Now, as they pass one another or as they go over one another, they superimpose and interfere, creating this temporary sum between the two waves. And so we're going to see that through this temporary sum of the two waves, we can either have constructive interference or destructive interference. On one hand, if the objects meet and they're both crest to crest or trough to trough, the sum tends to give us some sort of thing that is constructive. And so I should go even back here for a second here because I'm describing the first situation. If two waves meet crest to crest or trough to trough, then the sum of the amplitudes produces a larger waveform. And this is called constructive, or it sums together, it constructs, it builds together a wave. On the other hand, what we could see is if we have a crest to trough or a trough to crest that meet, the amplitudes are going to go against each other and they're going to battle each other and they're going to destruct or they're going to take away from one another. And we call this destructive interference. Now, suppose we have the following here. Let's start off with constructive interference with these situations here. This is going to be a positive amplitude or a positive pulse sent at a positive pulse. And the reference point is another way of saying, where do those two things meet? So we're going to say that this is also considered to be the meeting point of these waves. Now, as these things are sent towards each other, if this is constructive interference, we're going to say that if this represents some sort of energy 1, this represents energy 2, then when they get to the middle, it should be the combined total of these amplitudes, which I'm going to call plus plus amplitude, or the combined amplitude of these two things. We could also consider it to be the total energy, which is equal to energy 1 plus energy 2. So these things are summed together right in the middle. They all meet together or they construct together. But because of inertia, these things have some sort of inertial property where if they were moving with some sort of energy and some sort of amplitude, they're going to want to continue past this momentary point. Once they continue past this momentary point, here is where we get the one wave, here is where we get the other, or we can consider them, I guess, a separation of wave. And to be more specific, here's where that energy 2 goes, here's where the energy 1 goes. So the energy 1 is going to pass through this point. It's going to pass through the equilibrium point, or not even the equilibrium point, but the reference point where these two things meet. The E1 meets at the reference point, it passes through, and then it continues with its trajectory. Same with E2. It's heading towards the reference point, it meets at the reference point, and then it passes through the reference point. All right. Now, with destructive interference says, what if I have some sort of negative amplitude, which I'll make sure to write in here more specifically here. So negative amplitude, I have positive amplitude on the right. If these two things meet, supposing that they're the exact same, meaning positive amplitude, negative amplitude, then I'm going to get some sort of line that perfectly matches where the amplitude is equal to 0. And so maybe I'll backtrack that just a touch. Amplitude is equal to 0 in the case that these amplitudes are equal and opposite, and the energy total would be equal to 0 as well, because we're taking the energy of A on this side, or E1, we're taking the energy over here, and this balances out to be 0 if these are equal and opposite to one another. Now, there is going to be cases where in constructive or destructive interference that these amplitudes are not equal in magnitude, so you may get one outweigh the other. So you could even end up with something that in destructive interference may be a tad negative or a tad positive as well. That's definitely possible. But in the case of this, we're just really trying to re-emphasize that when you take these amplitudes together in destructive interference, they're going against each other. They're battling each other, almost like a tug of war. And if one is greater than the other, it will tend to go in that direction. But if they're equal, it balances out. Now, again, by that inertial property, that original energy is going to be sent through. Once it goes from the right-hand side, it then meets at the middle. It's going to want to continue through. Same thing with this one. Our negative amplitude, it's going to be sent towards the equilibrium, or not, I keep saying equilibrium, but it's the reference point, the meeting point. Once it gets to the meeting point, it just wants to continue through with that original energy it had. And so to be specific, here's my energy 1, here's my energy 2. Okay. Now, in summary, we've talked about what mediums are. We've talked about frequency, period, wavelength. We've talked about longitudinal waves. We've talked about transverse waves. It's a big section. The wave section is very big. And so when we move into two-dimensional waves, we're going to be adding even more to this. But what you need to do is start working on this assignment and just get as much practice as you can with these things. Answer as much as you can, ask questions if you have them, because there is a lot of conceptual pieces to this. And so you want to really master it and really identify where you may still not understand. All right, good luck with the practice.